right, everybody. Thanks for sticking around till 2:30. I know it's probably been a long day already to sit there and listen to people talk. We've heard about a lot of different topics. Hopefully I'll bring you something a little different than what you've heard so far. I will say that container runtimes are kind of the forgotten piece of a lot of the architectures we've been talking about. So I think I expect this mostly to be informational, some history. I'm not expecting you to make some decisions. Hopefully they've probably been made for you. But knowing that extra piece of information about the architecture, about how things are running in your Kubernetes cluster, hopefully will be valuable so that you get the full picture and understand what's happening under the covers. And so diving inside your pod, so to speak. I'm going to give you the most simple version of the Kubernetes architecture you've seen today. Everyone's talking about complexity. It looks super simple to me. You got YAML, you apply it, an app runs on some servers, you're done. Easy, right? There's no networking, no security plugins, no logging, monitoring. But the reason I want to start here is that this is what most application developers are thinking about from a conceptual perspective. They just want to make users happy. They want their application to be running, to be accessible, to be available, a lot of things that have been talked about. And hopefully you heard earlier, you shouldn't be typing kubectl apply, you should be using some nice GitOps or a framework that your organization gives you to deploy on your platform. But I just want to dive into what that, let's just talk about it as kubectl apply. It's that API to Kubernetes that you're introduced to at the very beginning of today. And you've already seen some of these pieces, the API server, etcd, a control plane node and some worker nodes. And there's this piece called the kubelet that showed up a few places already today. That kubelet is watching, again, this data store that has the information, that desired state that's been mentioned here, again, multiple times already today. The kubelet is what needs to make that reality. It needs to actually do something on that worker node to make something happen so your application actually starts running. And so those watchers are looking for the information they need to know. There's a new pod, there's a new deployment, there's a service I need to deploy. But there must be some piece they're talking about, they're talking to in this question, this red question mark. That piece is our container runtime. And when we talk about running containers, most people's minds are going to think Docker, because Docker's been around for almost 10 years now. And it's a thing many people use to learn, when they first ran containers, they learned a bunch of cool commands, Docker run, Docker ps, Docker stop. They learned how to build a container, to write a Docker file. And so this has been kind of the traditional piece of software that people have depended on, including Kubernetes. From the beginning, and someone mentioned the container wars, is it Kubernetes, is it Docker? Well, actually, Kubernetes has been using Docker since the very beginning. And so a worker node, as we dive down a little deeper, looks like this. This kubelet now has some way to talk to the Docker engine, to start containers, to do that lifecycle operations, based on its information that it got from listening to the API server to etcd to know that there's some containers I need to start, or there's a change I need to make in the configuration. This piece of software that sat between here, between the kubelet and Docker, was called Docker shim. And you'll have to go back several releases to find it in the GitHub codebase of Kubernetes, because it's no longer there. The Docker shim has been deprecated. There are a lot of blog posts in the last 18 plus months about that before the release where it was finally removed. But you can go find the Docker shim and see how the kubelet was talking through the Docker shim to ask Docker to start containers or pull an image. And also something happened in those intervening years. Docker that started as this sort of static binary you could just install, and it had everything. It had a build command. You could run containers. over time, that piece of software was decomposed into multiple projects. Containerd was donated to the Cloud Native Computing Foundation. Run-C, just that core executor, was donated to the Open Container Initiative. And so Docker was using these other projects to have this stack of capabilities that were implemented the things that you were used to just typing Docker run or Docker PS. I'm going to step back for a minute and say that, again, over time, Docker was not the only runtime available. Who's ever heard of Rocket or ever played around with Rocket? So it's also been archived. It's no longer an active project. But CoreOS created that in the early days of Docker. I just mentioned Containerd came out of Docker and was donated to the CNCF. Creo was created by Red Hat as an alternative that has its own suite of tools that you may have heard of, like Podman or Builda. And so there's been this growth in runtimes, and these aren't the only ones. The high-performance computing ecosystem has created some runtimes of their own. But in the early days, we really wanted to make sure, again, stepping away from Kubernetes and just thinking about containers, that we didn't diverge in what it meant to run a container. Because it'd be really painful if you switched jobs and had to learn a new technology about how a container gets built. There wasn't Dockerfile, there was some other abstraction. And so what we did at the time was create the Open Container Initiative project under the Linux Foundation. As you mentioned, I'm part of the Technical Oversight Board. I've been involved in the OCI since the very, very early days. Brandon here, one of the co-organizers, is also very involved in the OCI these days. Out of the OCI came initially two, but now three major specifications that give us that common substrate. The first was the runtime spec. So this is the definition of what does it mean that something is a container? What do I run? What are the environment variables? What namespaces do I isolate? Again, that's a bit of an overloaded term because, again, there's namespaces in Kubernetes, but containers themselves that run on Linux have a series of namespaces, the mount namespace, the PID namespace, the actual isolation mechanisms that make your container contained. So we had that runtime spec, and then the image spec is, well, how do I put that together in a bundle with the files that make up my container? When I build a Docker file, it turns into this set of layers. How do I represent that? And so the image spec gave us a way to do that in a common way that we can all different tools can package and translate and understand an image the same way. The third spec that was created years later after the initial OCI specs are the distribution spec, because again, most of us don't build images on our local system and then use them there. We want to transport them somewhere else. We want to push them to a container registry like Docker Hub or ECR or your cloud provider's registry or maybe a third-party registry. And so the distribution spec was the standard of how we do that. How do we talk to a registry? How do we pass layer information? How do we pull a manifest? So combined, these three OCI specifications gave us a way that all the common tools that say, I know how to build containers, I know how to run containers, I know how to annotate an image, if they follow these specifications, then they'll be compatible with other tools in the industry. So now walking back into Kubernetes, now we have these set of standards about how we can understand what a container is, how to run it, how to understand its configuration. And so one of the things we did back in the Kubernetes community is abstracted out this idea of the runtime itself. And so instead of that Docker shim, we now have the Container Runtime Interface that allows the kubelet to not have a direct understanding, this is Docker, I need to know the Docker API and the Docker command set. And instead, there's a set of CRI APIs that any runtime can implement and become a container runtime for Kubernetes. And the kubelet talks to that runtime over gRPC, and so the API of the CRI is protocol buffers over gRPC over a local Unix socket. Everything else remains the same. The kubelet is still talking to the API server, watching etcd to understand what it should be doing with the container runtime. Now, this isn't something new. This was actually introduced on the Kubernetes blog back in late 2016, so it's now been around for almost 7 years. But it's been maturing over time. And, I thought about trying to fit the whole CRI API on a slide. Didn't quite work. It's already too small probably for you to read from the back. But this is a subset of kind of the most common APIs, and many of them will make total sense, right? You want to run a pod sandbox, you want to start a container, you want to stop a container. There's really two services. If you can't read it, there's a runtime service with a larger set of APIs, and then an image service with just a few APIs around pulling images, what's the status of my image, removing an image. And so as you can see, the surface area of the CRI, fairly straightforward. It's all about that pod lifecycle, starting the pod, starting containers within the pod, deleting it, and then again, image management, the simple, pulling. Actually, I shouldn't say pushing, because you can't push images in Kubernetes. So yeah, pulling images, getting status, and then all the interactions with a container. So you want to exec into a container, you want to pull logs, you want to do port forwarding. All that is part of the CRI surface area. So if you decided tomorrow that you want to build your own container runtime, you can become a runtime for Kubernetes simply by implementing all of the CRI APIs. Today, Containerd has a CRI implementation, so that's the project that I'm a maintainer on. It's a CNCF project. Creo is also a CNCF project, also implements the CRI, hence its name, CRI-O. And more recently, Mirantis, the company that took the enterprise piece of Docker, because of the Docker shim deprecation, they've created their own CRI-Docker open source project, and so you can also continue using Docker as a runtime underneath Kubernetes by using the CRI-Docker shim. Now you might wonder, well, I used to know on my Kubernetes worker nodes that because Docker was running, I could use the Docker commands, if I had access to that node, I could go find out what's running. I could use Docker commands to maybe debug and understand what a container is doing, why something's stuck. Well, the CRI has its own command line that you can use to talk directly to a CRI. And again, now it doesn't matter what that runtime is, as long as it implements the CRI, you can use these commands to talk through the CRI to that runtime. One of the cool things is that you can actually play around with the CRI without even having Kubernetes installed. So I could take a Linux instance, I can install Containerd, I can install CRI-CTL. There's a user's guide in the Kubernetes SIG for CRI-tools. And I can actually deploy a pod without the rest of the Kubernetes infrastructure and see how that works, see how Containerd implements that, how it starts the pod sandbox and places containers within it. And therefore, it can also be an interesting debug or management tool on a worker node because you can, list the pods, you can see what images have been pulled, you can inspect a container, see what status it is, and look at all the configuration of the container, the environment variables, and all of that. Now, someone might ask, well, this is interesting. I understand kind of separating Kubernetes, the project, from this having a direct connection to a runtime. But why would I do that? And that's kind of a big topic that would be a whole separate talk. In fact, it's a talk I gave at KubeCon when I was younger and could talk faster. I demoed all of the available runtimes at one of the KubeCons, I guess pre-COVID, because it seems like a long time ago. But you can watch that and see kind of the trade-offs. And again, one of the interesting things here is that, I've mentioned the Containerd, Creo, and Docker are the three sort of main implementations of the CRI. Each one of them has some interesting configuration options to do isolation beyond just Linux containers. So who's heard of Kata containers project? Yeah, there's a few hands. So using like lightweight hypervisor isolation, you know, Amazon created Firecracker that's used by Lambda. Kata containers supports Firecracker as well as their own VMM that's based off the same core code base. Google has created gvisor, which is like a virtualization of the kernel syscall API layer. And so you might be interested in, you know, in some of the prior talks, there were discussions about, you know, is the container boundary enough? Do I have requirements for stronger isolation? And so you may be looking at, it's kind of nice that the CRI abstracts away, you know, the definition of how that container runtime is called, but maybe I'm going to configure my runtime to do interesting things like isolate each pod in its own hypervisor. And so this talk went into a lot of those choices you might have about additional isolation mechanisms. There's also, each of these runtimes may have different extensibility or pluggability that may be important for your use case. Maybe you're using through a cloud provider who offers some kind of extensibility or special capabilities with the runtime they're choosing to use underneath Kubernetes. But anyway, there's definitely interesting potentials there, including, just thinking of the last talk, Containerd now has a WASM shim. That Containerd can be used to run both containers, but also WASM images as well. And so there's a lot of work going on there to marry some of the Kubernetes concepts with WASM runtimes. All right, so it sounds like the CRI should be fairly static in that, you know, it just has a simple job to do the ability to start and stop containers, pull images, but it is a growing API. Over the years, there are new functions being added, and you might wonder, well, how does that happen? How do we change the CRI? And it's really similar to how the Kubernetes community operates in general, in that everything always starts with an enhancement proposal. And that's you going to the community and saying, I think Kubernetes should be able to do this. It needs to have a feature that, you know, enhances how storage is done or how CNI plugins work. And so that Kubernetes enhancement proposal process is you writing a proposal to the community, usually called a KEP for short. And of course, many of those KEP proposals may have nothing to do with the CRI. It may have something to do with a very different part of Kubernetes that doesn't require any changes to the CRI or how runtimes operate. But if it does require changes to the CRI, there's also a special interest group called SIG-Node that's all about that node-centric operation, what happens on the node, the kubelet, the runtimes. And so you probably will have to visit SIG-Node and talk to that community about your ideas about changing the API or adding something to the API. Now that there's three kind of runtimes that implement the CRI, you also need to go to each of those communities and get some commitment to add that capability to that runtime. So we're going to look at a few examples just to see how that works. Then, of course, as you add features to Kubernetes at large, there's obviously a maturity process that needs to take place, that your new feature goes through an alpha and beta and GA, and these feature gates are available, and in many cases will be turned off initially so that people upgrading to a new version of Kubernetes don't get new features that they didn't want. And so, you know, this is kind of the flow of how things happen, again, generally in Kubernetes, but also with things that impact the CRI. So a couple that have come downhill via Kubernetes into the runtimes, into the separate communities where the CRI is implemented, are checkpointing for forensic debug and user namespace support. User namespace support is interesting to me because back when I was contributing to Docker many years ago, I added user namespace support to the Docker engine. It's taken many years to figure out how to do that at the Kubernetes level because of all the interplay between runtimes and node-specific concerns and different runtime implementations of user namespaces. And so it's interesting that that has just now come into Kubernetes in a very recent release. But in both of these cases, and I can give you the slides, you can go read on these. You can read the enhancement proposals. Some of these took months, some took years. But again, the community rallies around to understand, is this the right path forward? How will people configure it? Is it secure? And so the checkpointing one was especially difficult because the initial idea was to allow checkpoint restore in general in Kubernetes, which has lots of interesting challenges if you've ever tried to think about doing live restore or moving to a separate node and restoring network connections and changing IP addresses. And so this one was actually scaled down to just be checkpointing so I can do some forensic debug on a container. And so that's what ended up being added. And so again, the author of this KEP came to Containerd, came to the CRI community, and worked out, how will we move toward implementation of this so when this is part of Kubernetes, your runtime will be ready to support this feature. And so again, on the right side, I took some quick screenshots of the FeatureGate web page of the Kubernetes docs. And you can see in the first column whether this is on by default. Many of these are false because they're newer features. What's the current maturity? And in the case, both of these are still alpha. And then what's the first release that this was available in Kubernetes? And so you can see this web page is growing because there's hundreds of feature gates now in Kubernetes. Some of them CRI related, and many of them are not as well. So in summary, I wanted you to at least understand that there's been this abstraction between Kubernetes, how it thinks about what it needs to run, and the actual runtime implementation. And this allows any runtime, any container runtime, to become a Kubernetes-supported runtime simply by implementing the gRPC API of the CRI. It is a stable and versioned API, and like I said, the core of it has not changed much in 7 years, but there are new features and expansion of features just based on the runtime capabilities that people need at the higher layers of Kubernetes, and sometimes that can be years of getting through that process and getting all the relevant runtimes to support that feature as well. So hopefully that gives you a little more detail on CRI, a little bit about the history of OCI and standardization of runtime capabilities at the CRI layer. And I think we have some minutes for questions, if there are, and if not, I'm here the rest of the day and happy to talk to you further. Thanks.
All right. Thank you, Phil. Okay, we have time for a couple of questions before we break for coffee.
Why there is less popularity on runtimes, virtual machine-based runtime, gvisor or K8s containers? Why those are not popular yet?
Yeah, so the question, why are those not as popular? First, there's obviously complexity. It's much simpler to just, use the container runtime to start containers. As soon as you have a hypervisor boundary, networking becomes more challenging, storage becomes more challenging because now, that hypervisor boundary creates isolation that you wanted, but now to get passed through for other things becomes more difficult. So some of those technologies are used by the major providers for, because they want to manage isolation. So I believe gvisor is used in various places in some of the GKE built services built on top of GKE. And then in AWS, Fargate has used Firecracker to isolate Fargate container processes. So they are used, and I believe GitHub Actions uses lightweight hypervisor isolation. So, you know, people sort of dig into these things and they say, oh, I saw a crash and I saw a Firecracker set of messages, so, you know, so-and-so must be using Firecracker. So I think there may be more use than we hear about, but it's definitely maybe not largely popular because of the complexities. You need to understand how you're going to surmount some of the challenges of further isolation that, you know, in the last talk, some of the reasons we moved away from VMs were because of the complexity challenges. Containers seem a lot easier. It's just a process on a shared host. So I don't know, you know, that there may be people here who've fought some of those battles and could also explain why maybe they haven't gotten widespread adoption at this point.
All right. Any more questions? Well, thank you, Phil, for bringing us back to sanity after 2015.